Hi, my name is Robert, and I'll be telling you about our work entitled Ideals, Determinants, and Straightening. This is joint work with Michael Forbes. So this is some work in algebraic complexity. So before I tell you what exactly our results are and what they mean, I first need to tell you about the model of computation that we'll be working with. We'll be looking at algebraic circuits. These are circuits that compute multivariate polynomials over your favorite field. So the internal gates of the circuit are labeled as either addition or multiplication gates. The inputs to the circuit are formal variables, and the output computes your polynomial. So for example, in the circuit on the slides here, the bottom left gate computes the polynomial x plus y, the bottom right gate computes the polynomial x minus y, and the top gate computes their product, which is x squared minus y squared. You can view this over any field you like. For the purposes of this talk, you can just think of it as taking place over the complex numbers. Now, these circuits, we're going to view them as computing polynomials syntactically. So they compute a polynomial as a formal sum of monomials. That is to be contrasted with, for example, computing a polynomial as a function, but it turns out those notions, at least over the complex numbers, they coincide. Now, there are two parameters of circuits that we'll be looking at, their size and their depth. We'll measure the size of a circuit by the number of edges present, and we'll measure the depth by the length of the longest path from an input to an output. Now, of course, in the circuit I drew, every gate just has fan-in 2, but if I restrict the depth of the circuit, we'll allow for gates to have larger fan-in. As a sanity check, the circuit on the slides here has size 6, and it has depth 2. So that's our model of computation. What questions are we going to ask about it? The typical question that one asks in this area is the following. I give you some large family of polynomials. So for every natural number n, I give you a polynomial fn in n variables, or maybe n squared or n cubed variables. And I ask you, how hard is it to compute that polynomial in terms of n? So this captures a large number of interesting algebraic questions. For example, you can frame the problem of computing the determinant or permanent of a matrix in this way. You can phrase matrix multiplication in this format. You can phrase iterated matrix multiplication this way, and other algebraic problems of interest. Now, this is a question that's been studied for a long time, for many different families of polynomials, for many different kinds of circuit classes. But this isn't exactly the question that I want to talk about here. I want to tell you about a generalization of this question, but in order to do that, I first need to recall the notion of an ideal in a commutative ring. So ideals are naturally occurring objects throughout algebra, but for the purposes of this talk, we'll just think about them as they relate to polynomial rings. So here's the definition of an ideal. This isn't perfectly general, but it works for our case. So an ideal is going to be generated by a set of polynomials. So we'll specify the ideal by providing a collection of capital N polynomials. What is this ideal? We'll denote it by putting the generators in angle brackets, and the ideal will itself be a set of polynomials. The way we form this set is as follows. For each I take the polynomial fi, and I multiply it by some other polynomial gi, and then I take the sum of all of these different products as I ranges from 1 to capital N. Now you may ask, okay, well, what polynomials gi can we choose here? You can choose any gi's you'd like. So the ideal generated by these polynomials f1 through f capital N is the set of polynomials you can write as a sum of multiples of the fi's. Now here's the modified question that I want to look at. Instead of giving you a family of polynomials, I'm going to give you a family of ideals. So for every natural number n, I'm going to give you an ideal of n variate polynomials. And your task is going to be computing one element of this ideal, and it better not be the 0 element, just to avoid trivialities. And the question is, how hard is this to do? I give you some set of polynomials, and now you just get to compute any one element of that set. And how hard is it to compute some element of that set? So this is a generalization because I've relaxed the specific thing that you have to compute. And we would like to understand this problem. And in general, what we would hope for is a characterization of the complexity of an ideal in terms of its generators. And in some cases, we actually do know that. So what do we know about this problem? So there's a theorem due to Kaltofen with subsequent improvements by Burgesser that at a high level says the following. It says that if G is in the ideal generated by F, then G is what I'll call F hard, meaning that if F is hard to compute, then G is also hard to compute. And the way that Kaltofen and Burgess are, attacked this question and really came about it to begin with is in the contrapositive. And the contrapositive of this says that if G is easy to compute, then so is F. And if you unwrap the definition of an ideal, it really just means that if a multiple of F is easy to compute, then F is also easy to compute. So really this theorem says that algebraic circuits can be efficiently factored. So already this problem of understanding the complexity of ideals with one generator, it's, aside from ideals being nice objects to work with and natural to investigate, it already has applications to polynomial factorization, which seems natural to study from the perspective of computer science. Now, of course, the question is, well, what can we say about ideals with more than one generator? And aside from just being a nice question to ask, this has applications to things like de-randomizing polynomial identity testing and proving lower bounds in proof complexity. And really, these aren't so much applications as they are equivalences. So we understand these ideals on multiple generators. We understand them in some instances by running these equivalences in reverse. But if I go out on the street, I pick up an ideal off the ground and I hand it to you, we don't really have tools available to allow us to analyze that particular choice of ideal. Really, everything we know in the case of more than one generator, it's kind of a convenient corollary of other work on other problems. So, we really don't know much about this question of ideals with multiple generators, and it seems like it has very nice applications and equivalences. This question was highlighted in a 2018 talk by Josh Grochow and in a subsequent 2020 article in the Bulletin of the EATCS. And in that talk and in that paper, he presents some very nice questions about this problem, some very general questions and some very concrete questions. And I want to tell you about one of the very concrete questions that he posed. So here's our setup. We have a matrix X, and it's an n by n matrix of variables. So every entry of the matrix is going to be a fresh variable. We're going to look at the minors of this matrix of size n over 2. So you take n over 2 rows, you take n over 2 columns, and you take the submatrix on those rows and columns, and you take its determinant. You do this for all choices of the rows and columns. You get many different polynomials, and we take the ideal they generate. Now, all of these generators, they're determinants. They're determinants on different overlapping sets of variables, and there are exponentially many of them. And of course, you would ask, well, what's the easiest thing in this ideal that we can compute? Now, and the reason we focused on the easiest polynomial is it's not hard to show that you can, in an ideal, find polynomials of arbitrarily high complexity. So really, we want to focus on what's the lowest complexity element of this ideal. Now, of course, there's the determinant, but maybe there's something in this ideal that's easier to compute. And the conjecture here is that there shouldn't be. So a little bit more explicitly, the conjecture is that there is some constant c between, say, 0 and 1, such that for every polynomial g in this ideal, computing g is at least as hard as computing a determinant of size n to the c. So this conjecture is that the polynomials in this ideal, they should be at least as hard to compute as the determinant, but maybe up to some small loss in the size of the matrix, and that's okay. Now, like I said, all the generators of this ideal are themselves determinants, and this seems like a natural thing to conjecture. The polynomials in this ideal also are tightly connected with matrix rank. The determinant is tightly connected to matrix rank. This seems plausible. Now, why am I telling you about this? Well, I'm telling you about this because we were able to resolve this conjecture in our work. And in particular, we confirmed the conjecture. So the main result of our work is we show that this conjecture is true for c equals 1/3, and it's true under a somewhat strong notion of reduction that I'll call a depth 3 approximate circuit reduction. Now, let me expand this box at the bottom of the slide a little bit and tell you in more detail what it is we proved. So I said this was some kind of approximate reduction. So we're going to have some approximation parameter epsilon sitting around. And then we're also going to have some polynomial g from this ideal. Now on the previous slide, this was the ideal of minors of size n over 2. Here we're just looking at minors of size r, where r could be n over 2, it could be square root n, whatever you like. Now, what are we going to do? We're going to try and reduce the task of computing the determinant to the task of computing this polynomial g in the ideal. So we'll have some subroutine that computes g, and we want to use that to compute the determinant. So here's the setup. Here's what we're going to do. We're going to build a circuit. As input, that circuit will take an m by m matrix of variables, where m is going to be roughly the cube root of r. The first step is that circuit is going to compute a large number of linear combinations of these different input variables. Then what we're going to do is we're going to feed those linear combinations into our subcircuit that computes the polynomial g. We do that, we take the output of whatever the g circuit computed, and we compute some linear combination of that and the constant 1. This gives us as output some polynomial that I'll denote as f sub epsilon of y. Now this is a polynomial in the y matrix, and like I said, it would be nice if this were actually the determinant itself. Now it won't be the determinant, but it will be very close to the determinant in a precise sense. Take the polynomial f sub epsilon and subtract from it the determinant of the y matrix. The result is some multivariate polynomial in the y variables. And the claim is that the norm of that polynomial will be at most epsilon. Now, what do I mean by the norm? Well, you can take any norm you like. For example, you could take the L2 norm of the coefficient vector of this polynomial. So what this is saying is that while we're not necessarily getting the determinant as the output of the circuit we built, we're getting something that we can push epsilon close to the determinant for any epsilon you like. You can make it arbitrarily close to the determinant. And in fact, the only dependence within the circuit on epsilon is going to be on the constants appearing on the wires. Right? The circuit itself won't, the topology of the circuit won't change in response to epsilon. So this is our main result is we can take any polynomial in this ideal, take a circuit computing it, add a little bit of extra hardware, and get something that's very close to the determinant. Now let me tell you one immediate corollary of this. So last year, there was this wonderful breakthrough result by Lamaya, Srinivasan, and Tavana, who showed that any constant depth circuit that computes the n by n determinant has to have size that is super polynomial in n. And in fact, not just any circuit that computes the determinant, but in fact, any circuit that computes the determinant plus some error term, some small order epsilon error term, that circuit still has to have this large size. Now, you take this theorem, combine it with the reduction from the previous slide, and you get the following corollary. We show that for any polynomial g in this ideal, of course, g has to be non-zero. Any constant depth circuit that computes g has to have size that is super polynomial in R. So we're taking their lower bound and we're extending it to a much, much larger family of polynomials. The lower bound quantitatively remains the same. So even though our reduction has this approximation built in, that's okay, because it turns out algebraic circuit complexity is very good at proving lower bounds even against that kind of approximation. So that's our main result, is we prove a lower bound for this ideal. And this is where we really didn't know how to address these questions about ideals with multiple generators prior to this work. So let me tell you a little bit about how the proof looks. So here's how the proof outline goes. So we've got some polynomial g in this ideal. Now what can we say about g? Well, of course we can say that g looks like this. It's a sum of terms fi times hi, where the fi are minors of the matrix, and the hi's are just arbitrary polynomials. And you sit and stare at this and you realize that this expression is somewhat difficult to work with because these hi's can be arbitrary polynomials. And this expression also may not be unique even. And so it's a little difficult because it's hard to rule out the following possibility. It could be that if you carefully choose the hi polynomials, that when you compute this sum, you get some massive cancellation and you end up with a polynomial that's very, very easy to compute. Now, of course, our theorem says that that can't happen, but a priori, it's not clear how to even rule that out. So what we're going to do is we're instead going to find a different basis of the polynomial ring, and we'll work in a different basis. And the reason for working in this different basis is things will be easier to manipulate, easier to understand, and we can actually prove something about this polynomial. Now, before I try to tell you a little bit about this alternate basis, let me just give you the 1,000-foot view of how the rest of the proof goes. So we found this alternate basis. That's going to be our step number 0. Step 1 is going to be, we'll find a change of variables, and in fact, a linear change of variables, depending on that epsilon, that will take our polynomial g and send it to some polynomial h plus an error term. And the gain here is that this polynomial h will still be in the ideal, but it will also be an element of our basis. And it will turn out that the basis elements will be very explicit polynomials. They'll be very easy to understand, and we can work with them directly. So we do that, and in step 2, what we do is we find some projection where we, in place of the x variables, we substitute the y variables. And there are some functions depending on epsilon here. And what this projection will do is it will send h to the determinant of the y matrix plus some error term. But it's okay that we accumulate these error terms. That turns out to be fine for our applications. So steps 1 and 2 are somewhat technical, and I don't have time to tell you about them here, but I can at least give a sketch of what this basis looks like in step 0. So a natural thing to try is, well, we could try the set of products of minors of x. We're working with an ideal generated by minors. We're working with the determinant. Maybe, if we express everything in terms of minors, maybe there's something to be gained here. And of course, this is going to be a spanning set because every variable is just a 1-by-1 minor. So of course, all the monomials can be expressed as products of minors of x. On the other hand, this is not a linearly independent set. If you expand the determinant by minors along a row or along a column, you get a non-trivial linear relation. Now, what we'll do is we'll find a subset that will turn out to be a basis. And of course, you could just take the monomials, but then we're back at square one. We haven't gained anything. So the thing to observe about the monomial basis is that you're always using products of minors of size 1. But instead, what we'll do is we'll use a basis where we try to take in every term minors that are as large as possible. And it will turn out that, for example, for polynomials in the ideal generated by R minors, every term in the basis will be divisible by a minor of size R or larger. So there will be something that we actually gain out of this. There will be some structure that we can work with. So let me try to give you a sense of what this basis looks like. So let me give you a definition. We're looking at products of minors. And I'm going to say that a product of minors is standard if, well, there are submatrices corresponding to each minor, and we'll say the product is standard if the larger submatrices appear above and to the left of the smaller ones. Now, of course, this isn't a precise definition. That's why definition appears in quotes. The precise definition is rather technical and would take some time to explain. So hopefully this will just give sort of a definition by example of what this basis looks like. So let me show you 2 standard products and a non-standard product. So here's one standard product. So I take a 3-by-3 matrix of variables, and I take the minor corresponding to the top left 2-by-2 submatrix, and the minor on the bottom right 1-by-1 submatrix. I take the product of these 2 minors, and I'll call that a standard product, because the larger submatrix is above and to the left of the smaller one. Another standard product would be if my first minor is on rows 1 and 2 and columns 1 and 3, and the second minor is on row 3 and column 2. Now, the larger submatrix is above the smaller one. It's not strictly to the left, but part of it lies to the left. So this is still okay. We'll still call this a standard product. Here's a product that's not standard. We'll take the minor on the top right 2-by-2 submatrix multiplied by the minor on the bottom left 1-by-1 submatrix. And here the larger submatrix appears above and to the right of the smaller one. So this is not a standard product. Now, in the precise definition of standard, we allow the submatrices to be overlapping. The rows and columns can be interleaved in different ways. You can have submatrices of repeated sizes. You can repeat a submatrix multiple times. The definition is somewhat technical, but roughly this is how you should think of it, is we take, we force the larger submatrices to appear above and to the left of the smaller ones. Now, why am I telling you about these standard products? Well, it turns out that there's this old theorem due to Dubile, Rota, and Stein from the 1970s that says the following. First off, it says that the standard products are actually a basis for the polynomial ring. So we've got some basis that consists of products of minors, and it's a basis that is not exactly the monomial basis. It's something else. Now, of course, there are other products of minors. There are the non-standard ones. And this theorem says that you can write a non-standard product as a sum of standard products. And in fact, their theorem gives a description of how a non-standard product is going to be expressed as a sum of standard products. And this is why we can work with this basis, is that not only do we have the basis, but we have some understanding of how terms that lie outside the basis get expressed within the basis. Now, these two pieces of information together are what's known as the straightening law, and that's where the word straightening in the title of our work comes from. So we express our polynomial in this basis, and we're able to do something with it. We're able to manipulate it and understand how it behaves under those manipulations and prove our theorem about this ideal. Now, how those manipulations go, like I said, it's somewhat technical, so I don't have time to tell you about it now, but this is the new tool that we're using in order to prove this result. So I told you that these results about ideals have some applications. Let me just give you a brief teaser of some of the other results that we have in the paper. So one other result we have is we give an analogous reduction for ideals generated by Pfaffians of a skew-symmetric matrix. And the Pfaffian of a skew-symmetric matrix is essentially the square root of the determinant as a polynomial. There's a similar straightening law for these kinds of polynomials. We give a similar result for the ideal. So now we've gone from understanding no ideals with more than one generator to understanding two different but related classes of ideals on multiple generators. The second other result we have is we have some lower bound on the dimension of the space of partial derivatives of polynomials and determinantal ideals. And you don't need to know what that means. What you should take away from this is that this dimension of the space of partial derivatives, this quantity and other quantities like it, are used in the technical guts of lower bounds for algebraic circuits. So if you wanted to prove some lower bound for this ideal, and perhaps our reduction doesn't work with whatever circuit model you're working with, maybe you can use this dimension of the space of partial derivatives instead. It's some other complexity measure, and we show that it's large for this ideal. Third thing we do is we give some constructions of improved hitting set generators for low depth circuits. And this is related to de-randomizing the polynomial identity testing question. And this is an analog of a pseudorandom generator for this particular setting. And finally, we give super polynomial lower bounds for the low depth version of Grotjahn-Patassi's ideal proof system. This is a proof system that operates with polynomials, with ideals, and naturally we have some applications there. So we give a number of different applications of this result, and I encourage you to check out the paper if you're curious about any of these. So zooming out, what do I want you to take away from this talk? There are three things I want you to remember. The first one is that we proved some hardness result for these determinantal ideals. And the main innovation, or the main interesting thing about this is an ideal, or a family of ideals rather, that has more than one generator. And this is really the first time where we picked an ideal up that has more than one generator, and we really understood it from first principles. The second thing I want you to remember is we used a quote-unquote new tool to prove our theorem. I say new, it's new to us, but of course it's almost 50 years old. And then the third thing to remember is, well, we gave a number of different applications of this result. So it seems like it's a very useful tool to prove other things in algebraic complexity. So these are the things I want you to remember. So let me end with a few open questions from this work. So the most natural open question is, of course, can we prove lower bounds for other ideals? Maybe there are other things like straightening laws or other related tools that we can use to prove lower bounds for more ideals. It would be nice to understand this question more. Second question is, our reduction was approximate, and in the proof we give, we really heavily rely on approximate computation. Is it necessary to use approximate computation in order to prove this result? And then the third question is, well, we found a new tool, this straightening law. Are there other applications of it to problems in algebraic complexity? It seems like it's a nice tool, but maybe there are other ways we can use it to resolve some other problems. So that's all I wanted to say. Thank you so much for your time.